Aye.
Yep.
Just make it a wee bit bigger. But so we were, the last couple of times we've been looking at people's channels and people's videos, and trying to dissect or show discernment and where these people are going wrong. But an equally good source of content is Wikipedia, just to look at it. So I thought if we looked at a few Wikipedia pages about the standard thought in science, then we can also pick out some of the fallacies and look at some of the sophistry which is being employed to define words and meanings in such a way that mathematics can be used as a tool of deceit, as well as one of great practical application. So whilst I am a fan of mathematics, I am very much aware of the capabilities that people have to do nefarious things with it. So so one of the Wikipedia pages here is something called the level of measurement, which is probably quite apt to the discussions we're having. And immediately what pops to mind is not to be confused with units of measurements or with level sensors, and we might just look into them afterwards. But the main thing that I want to say is that, and I'll maybe just preempt what we're going to look at, is that when somebody makes a measurement, or let me start again. So when you think about the scientific method, when you're supposed to make a hypothesis, go out and make experiments and observations to verify your hypothesis, or if it doesn't get verified, use that to refine your hypothesis. So whenever you say, observe something, record something, then you're talking about measuring it in some way, And this whole definition of what measurement means and what a measure is, and there's a whole science called metrology that is basically the science of measurement. And there's a huge history of mathematics behind it as well. What exactly you can measure, what is possible to be measured, and then what is a measurement and what does it actually mean? So what are you measuring? What's the geometry? What are you assuming? What tools, what instruments, what processes are you using? And all that plays a role. So if somebody says, hey, I've just had an experiment which measured and proved this, this, and this, then you really have to ask yourself, okay, what was he measuring? How was he measuring it? And get to the root of those assumptions. And this is what maybe this Wikipedia page and my breakdown of it will help people with.
I'll just pipe in. We use these Wikipedia pages just because they're a kind of common format of language that people tend to agree upon, and it's it's a kind of community thing so that we can relate things to each other that we're discussing. And we're not saying Wikipedia is the be all and end all. It's just simply a tool for these purposes.
Yeah, absolutely. Yep, it's just to help us make discernments here.
Yeah.
So the current kind of state, funny enough, of measurement has moved a little bit out of the sciences, and it's kind of defined now within the psychologist realm. A guy called Stevens has the best classifications that are widely adopted of scales and measurement, and what he calls is 4 different classes, right? Nominal, ordinal, interval, and ratio. And that might sound a bit scary, but when you actually go down to look at what this guy's saying, I think it's quite simple. So I'm going to jump down to this table here. And the first class of measurement is basically whether something belongs to something or not. So you're right, it's either equal to it or it's not equal to it. An example of that would be, Gavin belongs to the, members of men. So it doesn't tell me anything quantitatively about me. So it's not telling me anything about size, shape, form, or anything. It's just saying that I belong to a certain group, or I'm a member of something. So I'm either in it or I'm not. The second one, and this is very important, is this ordinal one, which is a matter of much contention and much discussion and argument at large, within the scientific community and amongst psychologists, is this idea of comparing something, a kind of ranking or a sorting. And what it goes back to is this idea of whether something is bigger than something or less than something. So I can say, for example, I am angrier than you, Dale. at the moment. Yeah. But it would be very difficult for both of us to actually quantify that. Yeah. So ordinal is one of these things where all you're left with, all you can really do is make a comparison and put them in kind of an inequality of some sort. Yeah, basically saying I am bigger than you, I am smaller than you, but you can't say how much it is. Yeah, and this whole thing, ordinal, is now a big focus in mathematics. Is basically on probability theory, which gets into all this quantum mechanics stuff. So when they say that something is bigger or smaller than something, then what they can do is draw a probability of it being bigger or smaller, but they can't actually quantify it exactly. You know? The next one is the so-called intervals of measure. So where you can find out the differences in things. So that would be, for example, degrees on a compass. I can split a compass up into 90 degrees. And I can say the degrees of difference between one direction and another one is a certain amount of degrees. Yeah. But so I'm basically just discerning the difference in things. And that's something that you can basically use in geometry, in circles, in astronomical observations, and a lot of visible observations. You look at the intervals. So the angular difference or the angular sizes of something. Yeah. And the very last one is the ratio. So this is the one where you can actually measure exactly how much it is in terms of a ruler, for example. So I can say something is 1 centimeter long, and I can say, good, this other thing is 10 times as big, so it's 10 centimeters. So where I can actually really quantify what is double of the size or what is half the size, so I can really quantify the relationship. So these are the 4 kind of measurement classifications that you have, or types of measurement that you can do. Yeah. Now you can see that ratio, this bottom one, where we're talking about the physical substances of lengths or magnitudes or things like that, are very much rooted in direct realism. Let's say, yeah, we can actually measure that. Intervals is where you're starting to invisibles, astronomical observations, those kind of things. And ordinal and nominal are very, very dubious, if you ask me, whether they should even be included in a definition of measurement. Yeah.
Oh, the 2 there that you just referenced last would be more a kind of subjective, assumption based.
Yep, absolutely. So this Wikipedia page goes into a little bit of detail about what nominal level is. Now you can see that, for example, speech, is one of the things that fits into the nominal type. So I can say there are things like nouns and verbs and pronouns, and either a word is a noun or it's not, or it's a verb or it's not. So it belongs to that group, if you like. Yeah. And that's all it can do. It can either belong to that group or it doesn't belong. An example of this would be a fox. You can put a fox in different classifications. Yeah. Now the mathematical operations, we've said, all you can really do is say it either is in the group or it isn't in the group. That's all you can really do. The ordinal scale is where it starts to get a little bit, as I say, how should I say, dichotomous, because this is where kind of opinions and consensus is tried to get. So if you take part in a consensus or an opinion or some research, then basically you usually get kind of 5 questions. Do you agree with this wholeheartedly, a little bit, none, not at all? You get kind of ranges that you can choose. Yeah, but again, it's not an absolute quantified amount. Yeah, there's nothing absolute about it, and it's something that's used very much in that kind of thing, market researches, but also in all the psychological tests that you do. Yeah. So if, for example, you're measuring people's IQ, you would do it with this kind of ranking. So, all you can do, for example, when you measure somebody's IQ is to rank them in terms of each other. You don't get a definitive score, if you like, or a quantity. Yeah. So these psychrometrics or questionnaires, these are all things that use this ordinal scale. And again, I would question whether that really is measurement as measurement should be defined. Yeah. I quite like Wikipedia, by the way. They seem to have done an update to something where if you hover on with your mouse, you get little pop-ups.
Yeah.
Which I think is quite cool because it saves you jumping from page to page and losing your place.
Exactly. End up with 400 tabs opened at the top.
Yeah, so, and again, I'll just step down through these ones just so that it becomes clearer. So an interval scale, this is one that measures the degrees of differences between things. Yeah. An example of that would be temperature, right, where we basically take two defined points, the freezing and the boiling point of water, and then we separate that into 100 intervals. And then we basically look at the ratios, but they're not meaningful because 20 degrees is not twice as hot as 10 degrees, right? All you're really measuring here is a degree of difference between items according to a graduated scale. Yeah? And the most important one then is basically the ratio scale, which allows you to really have a comparison of some quantity against some unit that you define to be the unit magnitude. You know, so if you say whatever, my ruler is 1 centimeter long, then you can go away with your ruler and measure other things in terms of that one ruler, or that 1 centimeter in that case, Now, there's, again, as I say, there's quite a huge bunch of debate on this, on whether this is the correct way to define measurement, and it has, you know, huge implications on how we perceive what measure is, what is actually a true measurement of a true value in an experiment. Because depending on the way that measure is defined, it's going to have a huge, how should I say, impact on the meaning that you interpret from it. I'm going to try and make this a little bit more clear. So, for example, when I assume a spherical Earth, and I say to myself, okay, I'm going to define straight lines as being the great circles on a sphere, then because of that very definition that I'm making, I also have to measure in terms of great circles or in terms of arc segments. If I take the assumption that it's a flat plane and I can use a straight ruler to measure things, then that's a completely different assumption from the spherical one. And it also means that I use a different measure, I use different instruments, and I use a different process to measure it. So you can see that measurement depends on the purpose of what it is you're actually asking. So if I'm asking the question, what is the shape of the Earth? It really also dictates how my measurement is going to be and how I define my measurement. So what I'm trying to say here, and I don't want to explode people's heads with too much theory, but you need to be very careful that when people say I measured this and that, and my measurements say that this and this is true, then you really have to be very discerning about what were the person's assumptions when he was making that measurement, which geometry did he believe in, or assume, so that, because these things play a role then in how the conclusions are interpreted. And that's this play on words at the end of the day then, you know, depending on your terms of reference and the sophistry that you use to present your conclusion, that's where people can be very easily brainwashed. So there's a couple of other things in this that I'm not entirely sure how deep I should go here, Del. Maybe I'm just pointing out to people that these are Wikipedia links that they might want to look at. There's obviously tie-ins to various other kind of things, and let me just pull up another page where we go then into the units. So not to be confused with the level of measurement or scale of measure, we now look at the units of measurement. So a unit of measurement is basically when you take a quantity that is adopted by convention or by law that is then used as a standard for measurement of the same kind of quantity. So people have now defined the meter to be, you know, the length of something, and that's the way we measure things now in meters, or generally speaking, in most countries. And all these weights and measures are standardized across multiple nations and countries. Again, we have everybody collaborating, yeah, and not fighting around standard weights and measures. And all these systems of units are basically being defined at an international level that, as far as I can see, are implicit in the deception. Because without that definition of measurement and that, how should I say, agreement, you wouldn't be able to make up the stories that they make up, and you wouldn't be able to tell the stories worldwide if you didn't have that international agreement. Yeah. So I think there's a lot of, how should I say, implicit working in those standards here of weights and measures, or in the science of metrology, that is trying to, how should I say, have these globally developed and internationally accepted units. Now, in the old days, if I had a grain of a sack of rice and I wanted to sell it to somebody, then I would usually stop at the toll booth of the city that I was going to, where I was going to sell my merchandise. And in that toll booth, the city itself would have a grain of corn, a sack, a sack of corn. And they would define that as the town sack of corn against which everything else got measured. So if you came with your sack, they'd put the two sacks next to each other, and you would then, that would be weighed and measured, and you would be paid according to the value of the town sack. Now all that's gone, so there is no weighting according to substances like corn or rice or whatever it is, copper, tin, metal. Now we have this abstraction to mass and units and standardized units, which, if you like, is obfuscating that tie-in that measurement should have to natural substances. And this page again is, has a lot of information about how that is done, and how I think it's something that always needs to be looked at. So basically this boils down to how certain ratios are basically hidden within units and measures. And basically all we're doing is expressing the relation between one number to another number, but we're hiding it very cleverly in all these units and definitions of measurements so that it's removed completely from the substances that we're talking about. It becomes all very abstract. Yeah, so that was basically, I don't want to jump into all these pages in too much detail because, it might just bore people rigid, and I don't want to do that. But if
it's not attached to a substance, you're measuring nothing, pretty much.
That's right.
So
that's right. It's made up stuff.
Which is why, when we say the luminaries, they're just an observation. They're just they're not tangible. There is no unit of measurement attached to it because you don't know what it is you're looking at. Yep,
absolutely. And visibles are basically always measured in degrees of difference. So that interval, you can't go out and measure a luminary with a ruler, right? All you can do is measure it according to an angular difference that you can see, using visible.
Yeah. And that's it, though. I mean, you still have to assume what it is.
Yep, absolutely. Yeah. Sorry, I'm kind of flicking through this page to see if there's something that I should address. I think one of the things that I did want to address was, this was quite funny. So a list of humorous units of measurement. Many people have made use or invented units of measurement for their humor value. So there's a few in here that are definitely worth a laugh. There's the one, a Sagan car from a tribute to Carl Sagan, which is supposed to be something that's technically 4 billion of something.
Billions, billions, billions.
There's a Mickey. They're definitely taking the Mickey out of us. There's one down here called a garn, which I thought was quite funny. Hold on, I need to get to this. Where the hell was it? There it is. Seasickness, garn. The garn is a unit used by NASA to measure seasickness and travel sickness caused by space adaptation syndrome. named after a senator who was frequently sick during tests. Yeah. A score of 1 garn means the sufferer is completely incapacitated. So I guess they're just making that up to make it sound more plausible, probably, you know, making up these wee stories. The other thing I wanted to pull back onto is this wonderful theorem here. Now, I don't know if people know this theorema egregium. Now, it basically means the remarkable theorem, which is a great name to give something, right? And what this theorem says is that you can determine the curvature of a surface from measurements made entirely on the surface, so that it is absolutely independent of whether the surface is embedded in a 3-dimensional Euclidean space or not. Now, Gauss called this theorem remarkable, and one of the reason he had to call it remarkable was that he started out with the premise that his surface was embedded in a 3-dimensional space, to then go on to prove that he didn't have to measure or know anything about the extrinsic space, and all he needed to do was measure stuff on the surface. Yeah. And that's why he called it remarkable. I would prefer to give the name bullshit to this theory, right? And I'm being an absolute heretic here because Gauss is revered as one of the prince of mathematicians, right? Yeah. But as far as I can see, what this man did was basically make up this mathematical sophistry to equate 2-dimensional spherical geometry with a 3-dimensional physical ball. Yes. So you've heard me saying this before, that when you look at the geometry of a spherical surface and that of a 3-dimensional ball, the geometries are absolutely similar. You can hardly tell them apart. But a spherical surface is really only a 2-dimensional object, mathematical object. You have to imagine it being unnecessarily, it doesn't need to be in a 3-dimensional space. It can exist for a mathematician without actually being in a 3-dimensional space. So if you think about a 2-dimensional surface, then there's no difference between that and a planar geometry. You've heard me talking about this before. I think that planar geometry and spherical geometry are just two different forms of the same thing. They're both 2-dimensional geometries, but you just have different definitions of straight lines. Yeah. But what Gauss did was basically manage to equate that whole thing to being a 3-dimensional ball that actually is then floating in a vacuum of space. Yeah. So that's where, if you like, the deception was taking 2-dimensional geometry and pretending it was really applicable to a 3-dimensional ball, in simplified terms. And this is also, it's quite an eye-opener, again, for anybody mathematically inclined, what the guy is saying. Again, I don't want to go into it in too much details, but it has so many applications to map projections, to the way that we do everything in terms of the geometry of surfaces, and that means all kinds of mapping and navigation and everything that we do when we look at things astronomical. Yeah. And the thing that ties into that one is then his very basic definition of curvature. And again, I'm not going to get into the maths here, because I always think it's enough to look at the basic assumptions behind it. Yeah. You don't need to worry about the maths, people. You'll see the fallacies already at the beginning. Yeah. That's where the problems lie in all these things. And it even says it here, you know, intuitively, curvature is the amount by which a geometric object, such as a surface, deviates from being a flat plane, yeah, or a curve from being straight, yeah, as in the case of a line. But this is defined in different ways depending on the context. there is a distinction between extrinsic curvature and intrinsic curvature. And this how should I say, artificial difference that these guys made in their mathematics allows them to get away with talking about a three-ball as two-dimensional mathematics and the other way around, so that they can go easily between planar geometry, spherical geometry, and making us believe that that is what is on a physical three-dimensional ball, yeah? And that all these things are the same. And they're basically just doing it by redefining the difference in mathematical definitions, yeah? There's one, if I find the word geodesic, there's actually quite a good lookup for that. Where the hell was it? Sorry, just bear with me for a sec. I'll find it. So Mr. Riemann. So geodesic, if you see this little pop-up here, geodesic is a generalization of the notion of a straight line to curved spaces. And basically what it does is it redefines a straight line on a plane to be the great circle on a sphere. And that's all it's really doing. It's a change in mathematical definition of the geometry. And when you do that, then you can basically go on to interpret what you mean in terms of spherical geometry. All your calculations will be correct. They'll be exactly the same as planar geometry, because the actual equations are based on the definitions, and you've changed the definitions, right? So you can continue to tell stories, let's say, right? I mean, it's as simple as that, right? You're assigning different words and meanings to the assumptions that you're making, and then you're interpreting your conclusions based on these new definitions, yeah? So, you know, this whole idea of changing a straight line to a curved line or to a great circle is basically the whole of science of geodesy, where people say that they are measuring the size and shape of the Earth using all these geodetic surveys, yeah? And that whole science is rooted in this basic assumption of going from planar geometry to spherical geometry by changing the definition of a straight line. And that's what I mean from my introduction when we were talking about the different levels of measurement, that you need to be very careful that when you're looking at the degrees of difference or the magnitude of something, then it depends very much on which geometry you've assumed. Because if you've assumed a straight line, or if you've assumed a great circle or an arc segment of a great circle, then you've got two very different ways of measuring things, yeah? And if you're not taking that properly into account, then you're making, you know, fallacies. You're making wrong judgments. Yeah. Good. I don't want people to lose the will to live just because I like mathematics. So I'll maybe just stop it at this point.
Much appreciated. I mean, it's part of the learning and understanding. As I say, I'm no mathematician either, so it's learning for me at the same time. So I think it's important for people to have, you know, other tools in their armory, you know. And that's it, you know, everybody's got their own place, expertise, and that just happens to be yours. So I'm more than happy to have you representing that.
I'm more happy to do my best to show what's going on.
I'll just be the understudy for that, you know.
Yep. I mean, there's just so much of that. I mean, we talk about it so often, you know, how words and sophistry and how rhetoric is used to bamboozle us. And what I'm trying to make clear is that it's very, very deeply rooted in mathematics, that same kind of sophistry. Not because mathematics is an inexact science, but just because depending on those assumptions and axioms that you make, you are going to be telling a different story at the end of the day. And your measurements are going to be different. So anybody who comes to you and says mathematics is a proof of why we live on a sphere, you can immediately tell them, no, it's bullshit. I mean, you say it all the time, the difference between natural science and formal science. And what I'm doing here is just trying to go a little bit deeper and show people exactly where that, how should I say, sophistry is. Yeah.